Hello again and welcome to episode 23 of Simply Electronics Basics. Today we're going to have a look at pulse width modulation, or PWM. Pulse width modulation has many different uses because it allows us to finely control different electronic devices. In this case, I'm pulse width modulating an LED, which means that I'm pulsing the power supply on and off at a certain frequency and with a certain pulse width. Pulse width modulation allows us to control the brightness of lighting, whether that's a standard bulb or LEDs, or it allows us to control the speed of motors. Pulse width modulation also allows us to make very efficient power supplies such as step-up, step-down and regulated power supplies, all known as switch mode power supplies. The switch mode in the name refers to the pulse width modulation technique. Now bear in mind that every circuit doesn't run fast enough for me to show you what the LED would do, but in this case the LED would actually dim and brighten depending on the pulse width that I'm sending to the LED. So let's just have a look at the power supply which I am applying a pulse width to. In this case, in every circuit, it's shown in a much simpler form. This would actually usually be some sort of microcontroller that is sending pulses at a certain frequency and at a certain width, turning a power supply on and off. So when this power supply is turned on, it's sending current through to this LED. And when it's turned on, its voltage when it's high or on is 3 volts. And when it's low, also known as off, it's 0 volts. So for every on pulse, there is 3 volts and 20 milliamps going through this LED, and for every off or low pulse, there is no current flowing through the circuit. In this case, it's pulsing every 1 millisecond, with a pulse width of 50%. The pulse width of 50% means that current is flowing through the circuit 50% of the time, and current is not flowing through the circuit 50% of the time. So the on time is equal to the off time. If I increase the pulse width to 80%, you can see the result on the graph at the top. Current flowing through the circuit is now on more of the time versus the off time. So the current flowing through the circuit is flowing 80% of the time during the pulse width, and no current flows through the circuit for only 20% of the time. If I further increase the pulse width to 100%, you can see what's happened. Because the pulse width is 100%, current is flowing through the circuit 100% of the time. So there is now no point in time where the circuit is turned off. If I decrease the pulse width to 10%, you can see that the circuit is off most of the time, and only pulses on very quickly 10% of the time. If I change the pulse width to 0%, you can see that the circuit remains off all of the time. The other thing to look at here is the frequency at which we're pulsing this circuit. Currently, we're pulsing it at 1 kHz. If I increase the frequency of these pulses, you can see that the pulses get much faster and appear shorter on the graph, although this is still 50% pulse width modulation. It's on 50% of the time and off 50% of the time. But now the frequency has gone from 1 kHz all the way to 10 kHz. And this means that we are pulsing this circuit 10,000 times per second. I can also slow it down by decreasing the frequency. You can now see that the frequency is 502 Hz, which means that this would be pulsing 502 times per second. In this case, when we're pulse widthing an LED, if we pulse it too slow, we would be able to see the visible pulses, which would not be ideal. So let's go on to a visual example of pulse width modulation using an Arduino to dim and brighten an LED. So here we are with our example of pulse width modulation on an LED. I have here a simple Arduino microcontroller. We will be going into the Arduino and many fun projects you can do with the Arduino in future videos, so make sure you subscribe for that. So we've got the Arduino microcontroller here, which is sending pulse width modulation to this LED. Now, I've got a little potentiometer here. A potentiometer is basically a variable resistor. So in this case, the potentiometer is used as a voltage divider so that we can get a digital value from 0 to 255 to change the pulse width to the LED. So watch what happens when I adjust this potentiometer. You can see that the LED is dimming when I adjust it, and I can also control the brightness. So by adjusting the potentiometer this way, I'm increasing the pulse width, so the LED is on more of the time, and by turning it this way, I'm decreasing the pulse width, so that the LED is off more of the time. And that's how pulse width modulation works. This can be done to control motors and even to create very efficient power supplies. So just note that this LED is not being dimmed in an analog fashion with a variable resistor. It's dimming through pulse width modulation through this microcontroller, which is sending those on and off pulses to the LED. It's just that the on and off pulses are so fast, within the kilohertz range, meaning it's pulsing at thousands of times per second. So the pulses are not visible to the human eye, but the effect of the dimming and brightening of the LED is visible to the human eye, because the LED, in this case, when it's dimmer, is off more of the time, and when it's brighter, is on more of the time. So in effect, it's changing the average voltage to that LED. And the good thing about this is that I can apply this not only to one LED, but I could use a series of transistors to apply this to much bigger loads, like huge high power motors. I can send a digital pulse width signal to speed the motor up and down. But we'll get into things like that in later videos. If you do enjoy my videos, make sure you subscribe for many more videos to come. You can also support me on patreon.com and get many more benefits when becoming a patron for Simply Electronics. The link to my Patreon page is in the description.